Well, forever, the idea of controlling the world with just a thought was something straight out of science fiction. But right now, a huge technological race is on to make that a reality, to build a direct bridge between the human brain and our digital world. So to really get our heads around all this, we're going to be guided by a big 2025 review from Luminous Applied Science and Engineering. They basically mapped out this whole new frontier, showing us who the key players are and what breakthroughs are pushing this all forward. You know, for so long, this idea of a brain-computer interface felt like it was 100 years away. It was the kind of thing you'd see in the movies, right? A dream about either getting back something you'd lost or maybe unlocking some kind of superhuman ability. But what if it wasn't just a dream? I mean, really, what if you could fire off a text message, play a video game, or just move a cursor across a screen without lifting a finger? Just by thinking about it? Well, that question just got a very, very real answer. Because in early 2024, what was once theoretical suddenly became real, with the very first human trial of a totally new kind of implant. And this wasn't just some small step forward. The moment was so huge that researchers are calling it a moonwalk, a legitimate giant leap for neurotechnology. So how did we get here? And maybe more importantly, who is the very first person to take that step? You see, this story doesn't really start with a piece of tech or a company. It starts with a person. It starts with the very first patient. So meet Noland Arba. About 8 years ago, a terrible diving accident left him paralyzed from the shoulders down. He couldn't move his arms or his legs. And what he says about the experience is it's amazing. He says the technology is so seamless, so integrated into him, that if he didn't remember the surgery, he wouldn't even know there was a chip in his head. It just feels like a part of him now. And with that implant, his entire world changed. In just a few weeks, he was playing chess online, moving the pieces on the board just by thinking about moving his hand. He got a piece of his autonomy back. Okay, so how in the world is this even possible? What is this technology that can do that? Let's take a look under the hood of the Neuralink implant. The device is called the N1 implant. It's a tiny, coin-sized computer that sits perfectly flush inside your skull. And honestly, the best way to think about it comes from Elon Musk himself. He calls it a Fitbit in your skull with tiny wires. So let's break that down. It has 64 threads, and each one is way thinner than a human hair. Those threads carry more than 1,000 electrode channels that listen in on your brain activity. All of that brain data gets sent out wirelessly over Bluetooth. It even charges wirelessly. And the whole thing is implanted by a custom-built robot that has micron-level precision. Now, the real game changer here, this secret sauce, is the material. See, older tech used these stiff silicone needles, kind of like a tiny bed of nails, that could actually damage the delicate brain tissue over time. Neuralink's big idea was to use these super flexible polymer threads that are designed to move with the brain and cause way less damage in the long run. But, you know, with any pioneering technology like this, the road is never perfectly smooth. The first human trial was, without a doubt, a huge success, but it also uncovered a pretty big challenge. Yeah, so a few weeks into the trial, they hit a snag. It turns out that most of those tiny threads, about 85% of them, had pulled back just a little bit from the brain tissue, and that caused a big drop in how much data the implant could actually read. But here's the cool part. The team just adapted. First, they tweaked the software, making it way more sensitive to the signals they were getting from the electrodes that were still in place. And that worked. They restored the performance. And for the next patients, they came up with a simple fix. Just implant the threads a few millimeters deeper to make sure they stay put. Now, while Neuralink gets a lot of the headlines, it is so important to remember they are not alone in this. There's a whole field of brilliant teams all trying to solve the same problem, and a lot of them are using totally different strategies. So who else is in this incredible race to connect the brain? Let's break down the competition. And when you look at the field, you see these fascinatingly different approaches. You've got Neuralink and Paradomics who go intracortical. That means their electrodes go directly into the brain tissue to get the cleanest signal possible. Then you have a company like Precision, whose subdural approach lays a super thin film of electrodes right on top of the brain. And then there's Synchron, which has a wild endovascular method that avoids open brain surgery completely. And this really gets to the heart of this central debate in the field right now. How invasive do you need to be? Neuralink's approach requires drilling through the skull, but in return, they get incredibly high-resolution data.
Synchron, on the other hand, threads their device up through a vein in your neck. No open brain surgery, but they have to trade some of that signal quality for a much, much safer procedure. It's a classic trade-off.
This technology is just moving at a dizzying speed. And with all of its incredible promise comes some equally huge challenges, both on the technical side and, of course, the ethical side. I mean, the entire field has to solve these problems. How do you make an implant that can last for decades inside a living brain? How do you protect the most private data imaginable, literally your thoughts, from being hacked? Who's going to get to use this technology? And maybe the biggest question of all, where do we draw the line between using this to heal people and using it to enhance them? And the ambition here goes way beyond just moving a cursor. Neuralink is already deep into a project they call Blindsight, trying to restore vision to the blind by stimulating the brain directly. People are also looking at using this to treat severe depression and all sorts of other neurological disorders. The potential is just staggering. So ultimately, it really feels like we're standing at a crossroads. We've built the tools to read from and even write to the human brain. The question that's left isn't just about what this technology can do, but what it will do to us. Will it simply restore us to who we were, or will it fundamentally redefine what it even means to be human?